Okay, this is the second hour of Physics 1C for November 22nd. Next, we're going to talk about the energy stored in an inductor. And for this, we're just going to use the idea of power. And we know that power is equal to current multiplied by EMF. So in the case of an inductor, where the induced EMF in the inductor is going to be negative L di dt. If we just look at the absolute value of this, so we just do EL absolute value, then we can write this as I times L times di dt. And then we can say that we know that the power is the rate of change of, or the rate at which energy is being stored. And if we think of the energy being stored in an inductor as some type of potential energy that we call U sub L, then we can say that this is going to be equal to IL times di dt. Then we can replace, we can get rid of the dt's. So this just says dul is equal to I times L times di. I guess if we're talking about the current at a moment in time and we're calling that I should actually probably use, these should probably all be lowercase i's too, since it's about current building up. So if we change these to lowercase i's, then we can just integrate both sides from 0 up to whatever current that we want to look at. So we could find the amount of energy stored in an inductor that carries a current I. And then over here, this is just going to give us the total energy. So the total energy stored then from this equation here, if L is a constant, is going to be 1/2 Li squared. So that is the energy stored in an inductor. You just take the current and you multiply by, or sorry, you take the inductance and you multiply by the current squared. You can kind of compare this. As I was saying, inductance is kind of like mass. Current is kind of like velocity, so you can compare this to kinetic energy. Because when the inductor stores energy, it's basically stored in its magnetic field. So if I have some coils like this here, and they carry a current that we call I, then there's going to be a magnetic field. And if this is the front over here, then the direction of that magnetic field will be this way. Right? And what we do is we say basically that the energy is stored in the field. Of the inductor. And the amount is this right here. And it is kind of a type of kinetic energy because you don't have the energy unless you have current. And current is, of course, a flow of charges. So in a very real way, it's the energy stored in the field as those charges are moving. And the inductor tends to want to keep them moving the way they're already moving. It always tends to oppose changes in current. Okay. Does that make sense? Kind of like a capacitor, right? A capacitor stores energy in its electric field. The amount stored, so like we look at a capacitor, so if I have a capacitor that has a charge Q, right, capacitance C, we know the energy stored in the capacitor is Q squared over 2C. This is stored in the electric field of the capacitor plates because there's an electric field here. If this is plus and this is minus, we know there's an electric field here. And in this case, the energy is stored in the electric field. Okay. So the next thing we want to do is to talk about magnetic energy density. This is something we're going to need when we talk about the propagation of light. So we do it now because we're introducing this concept. We might as well also introduce the energy density concept as well. So let's do that. So say that I take where we started, which is a solenoid. So I have a solenoid with an area A, a length L, some number of turns N. So I have a solenoid here. Let's say that it carries a current I flowing through its tubes like this. Out this way, in this way. And we want to find the energy per volume is what we're going for here. That's going to be what we call the magnetic energy density. We're going to use a lowercase u sub b for this. So the energy should be 1/2. Let's scroll down some. That what we just calculated right there. It's going to be 1/2 Li squared. And then we have to divide by the volume. And the volume is going to be A times L, right? We're now going to plug in L, which we derived earlier. L was N times 5B over I, which is going to be mu naught times N squared divided by L times, was it A? I think it is. And we multiply that times I squared divided by A times L. Be sure I got that right. Yeah, mu naught N squared over L times A. Mu naught N squared over L times A. So we're just plugging in for the inductance here. And now we can simplify some things. So what we end up getting is our energy density, UB, is now equal to, looks like this one cancels out with this one. And that looks to be the only thing that cancels out to me. So what we're left with is 1/2 mu naught N squared divided by L squared times I squared. But we know that for the solenoid, the magnetic field of a solenoid is equal to mu naught N over L times I. So the magnetic field of a solenoid squared would be equal to mu naught squared, N squared over L squared, I squared. If I divide 1 mu naught over here, then B squared solenoid divided by mu naught would be equal to mu naught times N squared over L squared, I squared. And that shows up in this equation here. So now we can say that our magnetic energy density is going to be 1/2 of the magnetic field of a solenoid squared divided by mu naught. But we can drop the solenoid part and say just in general, the energy per unit volume contained in a magnetic field is just the size of the magnetic field squared divided by 2 times mu naught. And we can compare this to something that we did earlier on, which is the magnetic field, the energy density of an electric field. And this one was 1/2 epsilon naught times E squared. We derived this one by using a capacitor, using the same concept. You can very easily get to this by just looking at a capacitor, using the energy stored in the capacitor right here, right? Dividing by the volume of the capacitor, and then just plugging in for capacitance, what we know, epsilon naught A over D, and you'll eventually get this relationship here. And we did that a long time ago. So here we go. We have the energy stored in the magnetic field is just the magnetic field squared divided by a constant, and the energy stored in the electric field is just the electric field squared divided by or multiplied by a constant, right? So we're going to see these concepts be applied today, but also more specifically when we talk about light waves. These are going to be very important, and talking about the energy that they carry per unit volume and stuff. And setting up this thing called the pointing vector, which will tie back to that video that I alluded to at the beginning of class. Okay, I went through that pretty fast, so I'll stop for a second. Does anyone have any questions? So what this tells us is that all magnetic fields have energy in them, and the amount is the size of the field squared and some constants. The energy per unit volume of the electric field is the electric field squared. Any questions at all? No? Oh, there's one other thing I wanted to mention. I was going to mention it when we were talking earlier, but we got... I went kind of long on this explanation. I wanted to look at something related to this. And I think for this, we can leave those on there, right? Your book spends a lot of time talking about the polarity of an inductor. So let's talk about that for a second here. In this open circuit right here, can you see that the potential difference across the inductor is 0, right? Let's see what happens to that as we close this here. Did you see what happened? I'll do it again. What happened to the potential difference across this when I close the circuit? Let me make sure of something here. So if this is black and this is red, is it positive? Yes. So if this is black and this is red, okay. What do you notice that happen? Watch what happens to this when I close the circuit right here. Tell me what happens. What was the initial value? Do you want me to do it again? It was -9, right? It's pretty much -9 if you look really quickly here. Let's do it again. All right, so we close it. It has an EMF of -9, right? Now let's see if that makes any sense at all. Let me open this again. Does that make any sense at all? So we've claimed that the inductor produces a self-induced EMF that is going to oppose any attempt to change the EMF in the circuit, right? So at the very beginning, when I close this, the EMF of this is opposite to the EMF of the battery, right? And you can see it in these little electrons here. At the very beginning, they're basically not moving because the EMF of this is opposite the EMF of the battery. Look at it again. This will go start off. It'll be a -9 right at the beginning. It's -9. And then as the current slowly builds up and eventually gets to full power here, right? What's the EMF of this going to be? It's drop. You can see what it's dropping to, right? You can see that it's slowly dropping to 0. And once this reaches 0, this object will be at full brightness right here. And we'll check that in a second. Once this one reaches 0, this one is going to be at 9 volts. We can check it now. See there, it's 9 volts. The sum of these two will always be 9 volts, right? But if this starts at -9, then this one's going to be at 0, right? And if this starts at... anyway, so your book likes to talk about the polarity of the inductor itself, right? So I'm gonna draw some things on OneNote right here, and I hope what I just did will help you understand what I'm gonna draw. To me, this gets to be just a little bit confusing, but I'm gonna attempt to do my best. Okay, when we talked about Kirchhoff's laws, right? So let's think about Kirchhoff's laws. Kirchhoff's laws and inductors, okay? I hope this doesn't go nowhere. I'm never very good at describing this. So if I have just a resistor, right? And I tell you that the current in my system is flowing this way, right? I've got a resistor here. What do we say delta V for this one's going to be? Is it negative IR or is it positive IR? Oh, I have to give you a direction. Suppose we go this way. Suppose this is A and this is B. It should be negative IR, right? And what that means is that in terms of the way that the book talks about this, I'm going to do this in 2 different ways because this is how I taught you all to do this in negative. Sorry, there's a negative sign right there. The way the book describes it is they would write it as VAB, the potential of point A relative to point B. Which is the higher potential here? Is it A or B? It's A, right? So VAB is going to be greater than 0, right? When I write delta V like this is like writing, in their notation, this is like writing the potential of V relative to A. And VAB would be the opposite of this. So VAB is positive, right? So the way that the book defines this is by saying that this side is positive and this side's negative, right? Okay. Now, if we put an inductor into our circuit, so I have an inductor here. So an inductor L. And if we say that we have a constant current flowing through this, so again, we'll put our same 2 points on here. So this is going to be A, this is going to be B. We're going to give this a constant current, I, like this. Now what we're going to say is that the potential of A relative to B should be equal to L times the time rate of change of the current, but if the current is constant, then what's this equal to? Zero, right? Okay, now let's go back to our picture and see if that's true. Looks true to me, right? The current is now constant flowing through here, right? We can even see it if we put this on here, that the current is in fact flowing constant, right? And in fact, yes, the polarity or the potential difference between these 2 points of our inductor is 0. Okay, so that's this makes sense, right? As long as the current's not changing, the potential's 0. The moment it starts to change, though, that's not true anymore, right? The moment it starts to change, that isn't true anymore, because the moment it starts to change, now the current's building up. There is a dIdt, so this is non-zero now. But it's changing over time. It's important to understand that, too. But when current is constant, like in a situation like this, the potential difference between A and B is going to be 0. That is to say, the inductor pretty much isn't doing anything at this point, right? It's not producing any like counter EMF or anything like that. Okay. Now, another possibility would be that I have my inductor, right, L, and I've got my points A and B, A here, B here. And let's say that our current is increasing, okay? So let's say that the current is flowing in this direction, okay? That's the direction of the current, but we'll use a little I to represent that it's like instantaneous current. And in this one, let's say that dIdt, okay, is greater than 0. That is to say that the current is increasing. Okay, now what does this mean? Well, now we should be able to say that the potential of point A relative to point B should be equal to L dIdt, but if the current is increasing, right? If the current is increasing, then what should this quantity be? Should it be positive or should it be negative? Okay. So that implies that this is the high potential point and this is the low potential point, right? And the part that I don't understand is the book. Underneath this, the book writes this. What does that mean? Do you all understand that? I understood everything that I said up until I drew that line. Is this to imply that this is the back EMF? EL? It doesn't use the L subscript, which is what's so weird. And it doesn't say... in my book, it's 995 in the bottom right, but it's going to be around there in your book. It's in section 30.2. I think this is the back EMF because if the current is in fact increasing, right, then there needs to be a back EMF here, right? But then the potential of A relative to B is still positive because the current wants to flow in that direction, right? The current wants to flow in that direction. So what I want to know is if we can take that idea and we can actually have it show up on our little thing here. Can I get this to where I can still see this? Let's do this. So let's see if we can make any kind of reasoning out of what's going on here. Let me just squish this down a little bit. So we've got our circuit here, right? We can see what the EMF is, and we want to set up a situation where, so this is the part I want to make sure I'm understanding. So if I go this way to this way, I get positive 9 volts. Let's open the switch. Let's discharge this. Okay. So if I start from here and I go to here, I see that there's positive 9 volts. If I start from here and I go to here, there's 0 volts because the switch is open. Why does it show negative? Am I actually supposed to write it like this? I don't understand that. If I go from here to here, let's do this. Let's go from here to here. Should this read positive 9 volts now when I turn it on? Yeah, it reads negative 9. Why is it negative 9? Do I really have to go from this side to this side to make it read positive 9? Ooh, I'm so confused. Because if I come down here and I go like this to this, that's negative 9. This is positive 9. And to make it positive 9, I have to go like this, huh? I guess that makes sense, because if this is the positive terminal, okay. This point's 9 volts, this point's 0 volts, is what that tells me. Now, if I come over to this, though, and hook this up in the same direction, right, that's 9 volts. Okay, so now we're clear that we have the same kind of... If I open this and we discharge the inductor, okay, what is this going to read right when we close it? It reads positive 9, right? Okay. Is that what this is telling us? Is that when the current's increasing, if I actually hook up a voltmeter here, like this, that it will read positive up until the current stops increasing? Which is what it's doing, right? Does that seem right to you all? Is that what this is trying to tell us? See, what this is telling us is if we were to measure the potential of point A relative to point B, that we would get L di dt. So this is going to be a function of the size of the inductor and of the rate at which the current is increasing. So the faster the current increases, the bigger the potential difference is going to be. But this is the measured quantity that we get right here, and we're seeing that it's positive, even though the EMF from the back EMF is negative. Does that seem right to you all? Oh no, I've crashed it now. I played with it too much, and it will not let me reset it, so we're actually going to have to close this to make it open again. Is that how you understand that? It says the potential difference across the resistor depends on the current, whereas B, C, and D, the potential difference across an inductor depends on the rate of change of the current. I don't know. I just don't know. So the other piece of this, just to draw the last picture to see if this kind of like drives this home for you at all. So the last picture would be, we take our circuit, we say the current is flowing in this direction, but now we say that di dt is decreasing. So now we have decreasing current. I'm spending a little bit of time on this because I want to make sure that when you go home to do your homework, I'm certain that there are questions in your homework that are like this, and I want to make sure that you can actually answer them. They ask about like which point is the higher potential and stuff. So we have our inductor L, and now with decreasing current, the idea would be that the back EMF is now going to actually drive the circuit to keep the current going in the same direction. So now this is going to be our EMF associated with the inductor. But now if we look at the potential difference between the 2 points, VAB, which should be equal to L di dt, now if the current is decreasing, right, then we can say that that this is going to be less than 0. And that we can check on, well, we can't do it anymore because I'd have to redo this actually. But we can do that though. It did look like when we opened it that the value that it was reading was negative. That's what I saw, at least. When we took our... let's see if we can do this here. Current. Okay, light bulb up here. Wire. Light bulb. Inductor. And then some more wires. Okay. And then now what we need is this one. Voltmeter. And we need to put it so that it's here to here. Okay. So the claim is that when we close it, it's positive, and it is. And then when we open it, wait, why isn't this dropping to 0? Oh, because this isn't connected. Oops. Can we pause it? Let's pause it. I want to put this wire connected to that. There we go. Okay, let's discharge this. Let's try this again. There we go. Now it's working. So it is positive now. The claim is that if we made the current decrease through this element, which we do by opening this, that it should now reverse polarity. Right? Isn't that what this is saying? That now the potential of point A relative to point B should be negative? Right? That this is now going to be the negative side and the other side is the positive side? Right? This is negative and this is positive? Okay, let's see if that's true. So if we watch this right here, the claim should be that this should now start to read a negative value when we open this. So let's open this on 3, 2, 1. And it does, it reads a negative value. So they're right from the perspective of actually checking this. I don't know what, like, I don't know why they place an importance on this. There's this whole discussion of like non-conservative and conservative fields and stuff. But I do know that in your homework, one of the questions that you're going to get asked is, which side has the higher potential? Is it A or B? And this should hopefully help you to solve that problem. At least I hope so. All right, so we just talked about magnetic field energy. I think the next thing we're going to be talking about is RL circuits. I apologize that there are some topics in physics, and this doesn't just apply to physics 1C. It also applies to when I teach 1A and 1B. There's certain topics like this that I don't really understand very well. And I'm not going to stand here and try to pretend that I do. And that's why I kind of like muddle my way through these type of explanations, is because I want you to understand that even though I've studied a lot of physics, it doesn't mean that I'm able to interpret the textbook any better than you are. You know what I mean? I feel like I have a good conceptual understanding of the way that inductors work. I don't have a great understanding of what's going on with this, or why do they see it as being important to tell you this, you know? Why is it important to understand that this is positive, and this is negative, and this is negative, and this is positive? For me, it's not that relevant. Maybe for an engineer, it is really relevant, you know? I just don't know, but I just want to say that I don't know everything, and I'm not going to pretend like I know everything. I'm just trying to do my best to show you how I would work through trying to understand it, so that you can use your own logic to try to help you yourself work through and understand it, right? That's just how things have to go sometimes. You just have to kind of like work your way and try to understand what's going on. Now, it is going to be helpful to the derivation we're going to do here in a second, though, so that does have that going for it. Okay, we now want to talk about an RL circuit. So an RL circuit, I think I copied the picture from the book for this one. Let me see. Did I? I did. So here is our RL circuit. It's very similar to the circuit we were just looking at, that we just looked at on the FET diagram. Okay, so let's look at the circuit. In our circuit, we have an EMF source, we have a resistor, we have an inductor, and we also have a secondary switch and this branch right here as well that we're going to use for the second half of what we do. For the first half of what we do, we're just going to be looking at this portion of the circuit right here and saying that we're going to close the switch S1 at t equal to 0. Okay, so I'll draw my own circuit on here too. But for the first half, all we're talking about is I've got an EMF source, I've got a resistor, I've got an inductor, and I've got a switch. And we're going to say basically that our switch here is going to be closed at t equal to 0. And this is our EMF source E. When we close our switch, as a result of that, there's going to be current that's going to flow in our circuit. It's going to try to flow this way. But because of our inductor L right here, that inductor is going to make it so that the current doesn't instantly reach its max value. And what we're going to do is we're basically going to do a little bit of a loop rule here. And we're going to start from this point right here and say that as we go from this point to this point here, can you all tell me, do we get positive if we're going in this direction in our loop, right? Do I write down a positive E or a negative E when I go from the negative side to the positive side here? Positive, so we'll have E. And then when we get to IR, you all told me that this is going to be negative IR, right? So minus I times R. And now the question becomes, what do we put down for the inductor? Now, I titled this part right here, Kirchhoff's laws and inductors, because we want to be able to use Kirchhoff's laws for inductors. And so here are the rules. Those are basically the rules right there. In this case, the current is increasing, right? That's the situation. So if we call this like point A and we call this like point B, right? Then I think we want to write, because we're going from A to B, right? I think we want to put a negative sign, right? God, this is so confusing with the way they define this stuff, but it does work this way. So I'll try to, so this would then be, I want to say negative L di dt. So why did I put a negative sign there? My reasoning is that if the potential of point A relative to point B is positive, right? That's what this says. Then really what we're writing, here, let me go back up one step to show you what I mean by this. You see this right here? Where for our current through the resistor, when we do Kirchhoff's laws, we always write negative IR, right? But if I actually want to write down what is the potential of point A relative to point B, right? If this is positive and this is negative, and I go from, if my loop direction is like this, right? If this is my loop direction here, going to the left, I'm going from high potential to low potential, so the change in voltage, delta V, is still negative I times R, right? So if I were to apply the exact same concept to these three right here, I would say, in this case, delta V is 0. In this case, I would say delta V is equal to negative, I don't have enough room. Oops. I would say delta V is negative L di dt. And in this case down here, I would say delta V is equal to positive L di dt. This is what I find so confusing about this type of notation, is that the primary time in which you're going to be using this stuff is Kirchhoff's laws. So why would they give it to you in this form? Do you see what I mean? This is so confusing. Why don't they just write delta V equal to negative L di dt? This makes sense. Di dt is positive, so this thing's negative. And what do I mean by negative delta V? I mean, you're kind of going downhill. And if you're going downhill, that means that potential of A is bigger than potential of B, right? This means that VA is greater than VB. And the way that it's written is VB minus VA equal to delta V. Am I just confusing you all? I hope not. I find that the book is being confusing, and I'm trying to demystify what they're doing, but still allowing you to be able to go back to the book and kind of like understand why what we're doing in class looks a little bit different than what they're saying. Yeah, exactly. Right? That's all it comes down to. Mystery user account / Michael. Exactly. Like, if we're going to put negative IR for this, right? Well, why do we put negative IR? We put negative IR because we're going downstream, right? We're going from the high point of potential to the low point of potential. And of course, we're doing the exact same thing here. We're going from high potential to low potential. So that's where the negative sign shows up. Anyway, okay, so equals 0. Again, I'm trying to allow you the ability to at least look at the textbook and gain something from it. I know a lot of you aren't going to look at the textbook at all, but for those of you that do, I want you to be able to look at it and understand what they're saying compared to the type of notation that I use, because I vastly prefer this type of notation over this type of notation. I just like it a lot better. Anyway, so given that this is our equation, well, this is going to be a differential equation that we can solve, because we have a current I, and we have a di, and we have a dt. So let's do what we normally do with these type of things, and let's separate variables. So we're going to write this as E minus IR is equal to positive L times di dt. And let us multiply dt over here. So we're going to have dt is equal to L times di divided by E minus IR. And now I think we're going to multiply by R over L. We can also multiply by a minus sign, but who cares? Yeah, we should not do that. So multiply both sides by R over L. So what we're going to get on the left-hand side is R dt over L. On the right-hand side, this L will cancel out with this L. And I'm basically going to multiply the 1 over R into the denominator down here, so that what we're going to get is di E over R minus I. Okay, because multiplying by R over L is the same thing as multiplying by this. This may be actually easier to understand. If I multiply by 1 over L over R, that's the same thing as what I just did. And then you can see that this L cancels out with this one. If I multiply E through here, I'm going to get E over R, and then IR times 1 over R will be just I. Should I multiply by a negative sign too? Sure, why not? Let's multiply both sides by a negative sign. So now the left-hand side is going to be negative R over L dt, and the right-hand side is going to be di. I'll just multiply the negative through the denominator, I minus E over R. And now what we can do is we can do a little integral. We will go, time started at 0, right? S closed at t equal to 0. So we'll go from 0 up to some time that I'm going to call t prime. On the right-hand side, we will go from 0 up to some arbitrary current that I'll just call capital I. I guess we should stay with the theme of lowercase I being instantaneous current. We'll go to I prime. Left-hand side of our equation is just going to be, well, does resistance depend on time? Usually probably not. Does inductance depend on time? No, because what did inductance depend upon? I'm going to write down the inductance of a solenoid again here, because I don't think I ever really talked about it very much. The inductance of the solenoid was mu naught number of turns squared over L times A, right? This just depends on basically just geometry, right? It depends on the shape of the conductor in terms of its area. It depends on the length of the inductor, and it depends on the number of turns in the inductor. So the question is, how is it shaped, basically? That's all that this depends upon. So L definitely doesn't depend on time, and so it doesn't depend on I. So we can go ahead and say that the left-hand side of this equation just becomes negative TR divided by L. Oops. TR divided by L. This is T prime. The right-hand side of the equation is going to become a natural log function. It'll be the natural log of I minus E over R. Minus the natural log of negative E over R. And then we can combine these two together. So we'll get negative TR divided by L. Oh, I should have put I prime on both of these two, because the I prime was the, is equal to the natural log of, we'll drop the primes in this line, I minus E over R, divided by negative E over R. And then this is going to be equal to, I'm now going to multiply the negative sign back into this equation here. So we'll have the natural log of E over R minus I divided by E over R, like that. We'll raise both sides to the e power, so we'll go e to this side and e to this side. So on the left-hand side, we'll get e to the negative tr divided by L. And then on the right-hand side, we're going to get just e over R minus I divided by e over R. Multiply this to the left-hand side. So we'll get e over R, e to the negative tr over L is equal to e over R minus I. Our goal is to find I as a function of time, so we're nearly there. We just need to add I to this side. This will give us I as a function of time in our circuit, and it will be equal to, there's going to be an e over R minus e over R, e to the negative tr divided by L. Factor out the e over R from the right-hand side. So we're going to have e, or I of t, is equal to e over R, which is the maximum current, multiplied by 1 minus e to the negative tr divided by L. And this will give us the current as a function of time for when the current is turning on, basically. Okay? When the current is turning on. How does the book put it? Did they give that name to it? It just says current. Yeah. So this is it only when it's turning on? I think so, because I think when it's decaying, it's going to be different, right? So this is going to be current growth in an LR circuit. And it has a very similar look to the equation that we get from the RC circuit, right? I'm also going to say that E over R is also known as the maximum current, so we'll just call that I max times 1 minus e to the negative tr over L. So yeah, so it looks a lot like the equation that we got for charging a capacitor, right? So you could think about this as a way of like charging an inductor. You're not really charging an inductor though so much as you're giving it a magnetic field type of energy that you're giving to it. But this tells us that that current does not instantly rise in your circuit, and in fact it takes some time. And if you plot the current as a function of time, it's going to look something like this. At I equal to 0, what do you get? Let's check the limits here. What's I 0 equal to? Well, that's going to be I max times 1 minus e to the 0, which is equal to 0. So at t equal to 0, you're going to get 0 current, right? But then the current will slowly grow and will eventually kind of level out and then asymptotically or eventually approach the maximum current value up here. So that's going to be your asymptote, basically. And that's what it's going to look like. If we plug in I as t goes to infinity, then what happens is you get I max times 1 minus e to the negative infinity, but e to the negative infinity is 0, so you get basically just I max, and that's how you know that this is the right kind of curve for it. It slowly approaches that maximum current. You don't have any questions? Does that all make sense? We've done this kind of thing before, so I guess I would understand if it makes sense. So let's define tau to be equal to L over R. We're going to call this our time constant. It's going to give us a way to understand, exactly how long it takes for the current to build up right here. And, just like with our RC circuit, if I say right here that this is equal to the time that's 1 tau, then at that moment in time, the current is going to be about 63% of maximum current. And you can see that pretty easily if we plug that into this equation right here. Did I do it right? L over R, right? Yeah, okay. If I plug I of tau, right, I'm going to get I max times 1 minus e to the negative t, well, if t is tau, then t is L over R times R over L, which is just 1, right? So you end up getting 1 minus e to the negative 1, and 1 minus e to the negative 1 is approximately equal to 0.63. So this is how you get 0.63 of I max. And that's, yeah, we call that the time constant for the LR circuit. It's L over R. That means that the bigger that L is, the longer it's going to take for it to charge up, right? And the bigger that the resistance is, the slow it's going to charge up more. Yeah, the bigger that this is, the faster it's going to charge up, actually. Let's see if this makes any sense. Now, we can see it visually. I showed it to you visually earlier. But we can see it pretty visually here, that if I have 50 henries here, how much can I change the resistance? I can change it quite a bit. So 50 henries here. Let's change this down to a kind of a smaller value. Let's make it 20. Okay, so if this is 20, and this is 10, what's L over R equal to? So 20 and 10, what's L over R? L is 20, R is 10, what's L over R equal to? It's 2 seconds, right? I'm going to show you a couple other things here just to kind of point some things out real quick here. So if you do I of 2 times tau, okay? 2 times tau, what you're going to get is 1, oops. So let's just do it like this. E to the negative 2 minus 1. So we're going to get, this is going to be 86%. So this is going to be 0.86. If you do 3 tau, you're going to do 1 minus e to the negative 3. This is 95, so this is 0.95 of I max. And if we do 5 tau, now we're at 99.3, so this is 0.993 I max. So by this point, it should be fully charged, right? Pretty much. 99% charged, right? So you all told me that here, if I have L equal to 20, and this equal to 10, we get a value of 2, right? 2 seconds. So if we take 2 seconds, that's this number, right? And we multiply by 5, it should be 10 total seconds that it takes for the current to reach maximum value, right? Let's see if that is true. We can actually throw a current chart on here to tell us if that's true or not. So let's drop it on there. Let's see if, in fact, it takes 10 seconds to reach max current. Let's see if that's true. I'm going to wait till this hits 1340, and then I'm going to close the switch. Okay, it just did it. So I'm going to wait till the 1345, actually, so it's going to be there. A little bit before it. So it should be at 1355 that we're at max. Let's see. Pretty much already there, right? Still got a little bit, though. Still got a little bit. And there, boom. Almost completely gone. Right? Okay. So let's start over again. Let's discharge this. Now, if I were to make this, let's say, smaller, like 10. Now, what is the what's our time constant now? What's L over R? Remember, this is L, and this is R. So what's L over R? It's 1. So if we do 5 times 1, it should take about 5 seconds for this to fully charge. So let's see if that's true. Next one's 1390. I'll start it at 1395. So there's 92. There's 95. It should take 5 seconds. So when it gets to about there, it's done. Or almost done, right? Okay, so can you see how this quantity is kind of helpful in understanding just how sluggish the circuit's going to be? We can go back to the extreme. Let's just see how the resistance affects it. So let's leave the inductance really small. What's going to happen is I increase the resistance here. Like, let's say I make the resistance 100, and let's change this to 50, or let's do like 30. Okay. All right. So what is our L over R now? What is L over R equal to now? .3, okay? So if we take 0.3 and we multiply by 5, we get 1.5 seconds, right? So that implies that this circuit should almost be fully charged up. That is to say that you get the full magnetic field inside of here in about 1.5 seconds. Let's see if that's true. Yep, really fast. So fast that we really can't even keep track of it, honestly. But if we close it and watch this right here, it will start off at 9 and then just drop almost instantly in about 1.5 seconds all the way down, right? So now the question becomes this. Why would the resistor have any effect on how long this takes? Why does the resistor show up in this equation at all? It certainly makes sense that the inductance should show up. And does it also make sense the inductance shows up in the numerator right here, which implies that the bigger that the inductor is, the longer it takes to charge up, right? We're multiplying by 5 because that's about the amount of time that it takes to get to 99% of max current, right? If we just multiply by 1, it's going to be about 63% max current after 1 tau. After 2, it's all about just plugging in. I guess an easier way to look at it is this. That equation, if we write it in terms of tau, is I of t is I max 1 minus e to the negative t over tau. So 5 tau is 1 minus e to the negative 5 tau over tau, which is 1 minus e to the negative 5, which is... That's where I got that from. Okay, so again, does it make sense to you all that t is directly proportional to L? That is to say that the time that it takes for it to fully charge up is proportional to how big this is, right? Yeah, that makes total sense. Okay. What about the denominator, though? Why is it that it seems that the bigger the resistor is, the faster that it charges up, and the smaller the resistor is, the longer that it takes to charge up? What do you think? Why is the R in the denominator? Does the resistor prevent the current from reaching the inductor? Well, it certainly decreases the magnitude of the current, right? Because what's the max current in this circuit? If it's 9 volts and it's 100 ohms here, right? Then 9 divided by 100 is like 0.09, about 0.1 amps, right? Whereas when this was only 10 ohms, the max current was like 9 amps or so, or 10 amps. Does the resistor prevent the current from reaching the inductor? I don't know. I actually don't know the answer to the question I'm asking you, at least not immediately. I think we got to kind of think about the effect that the resistor has on what I would say is if it lowers the total current flowing through the circuit, right? If it decreases the total current flowing through the circuit, then doesn't that mean that the size of the magnetic field that's produced inside of this is smaller? Does that sound right? The size of the magnetic field that we get inside of here is going to be less, right? Do you all understand what I'm saying? If the current, by increasing the resistance, you decrease the size of the current. There's no way to stop the current from reaching the inductor, by the way, Josh, not at all. It just makes it so that the rate at which the electrons are flowing by it is kind of smaller. Anyway, I think you would all agree that by changing the size of this, we change the current flowing through this branch, right? And I mean, you can even see it if we just open this, discharge this. If I reduce this down to like 10 again, right? And then we close it. Notice that the electrons are flowing much more quickly now, right? That's because that's what the resistor does, is it slows down or increases the speed at which these things are moving. So when we compare what was happening there, where we have this very fast current flowing through our inductor here, then the magnetic field that's produced here is going to be proportionally just as big, right? Because the size of the magnetic field of our inductor is mu naught N over L times I. It's directly proportional to the current flowing through here, right? So if I change my resistance here to be like 100, and then do this, now the size of the magnetic field here is much smaller, right? It's smaller by a factor of 10. And if the size of the magnetic field is stronger, we can go all the way back to the beginning of what we talked about at the beginning of class today and say that, you know, the induced EMF, right, is proportional to the rate of change of the flux here, right? And so if the size of the magnetic field itself here is smaller, then doesn't that mean that the rate of change also has to be smaller? Is that true? It is, right? Like, just from if we compare this side to this side, if B is smaller, which is part of this, then E has to be smaller too, right? It's B dot A, exactly. The area of the conductor doesn't change, but the size of the magnetic field changes, then that could have an effect on the overall back EMF. And I think that's what's happening. I think it's that if the size of the current is really small, then the inductor here isn't going to have nearly as much flux through it. And if it doesn't have nearly as much flux through it, then the rate of change of the flux is going to be smaller. That's the part about it I'm not sure about, that last part. And then as a result, I don't know. Does that seem reasonable? Just trying to, again, to go back to what the question that I'm asking and trying to resolve is why does the resistor show up in the denominator down here, right? I don't know. I don't know if that explanation I gave made any sense. Does that make any sense to you all? R affects the size of the flux because it affects the size of the current, which affects the size of the magnetic fields. Not sure. Can anyone else come up with another explanation as to why the resistance shows up in the denominator there? We really need to take a break here too. How does current affect mathematics? Oh, here, I'll put all the things on the board here. Okay, so let's put all the things together. That's a good idea to do because I forget that all this stuff is in my brain because I had to memorize all this stuff at one point in time. So the magnetic field inside of the inductor is basically, let's just say it's a solenoid. That's the easiest thing to do. It's mu naught N over L times the current. So there's the current showing up right there. The flux is defined as B times A, and the back EMF, EL, is d phi b dt. So that's how they're all connected together. So if this is lower, then this is lower, which means this is going to be smaller, which I think means this is going to be smaller. That's, yeah, it's probably a lot easier if I write all the equations on the board. Okay, so I think that's why the resistor shows in the denominator. I could be completely wrong, but that's at least the first thing that I think about. There's also current decay in an RL circuit. I'll let you all figure that out yourself. We need to take a break because I want to make sure that we cover LC circuits. I think that's the last topic from this, and we'll be done. So we'll come back. We're going to do one problem. In fact, I'll put the problem on the board, and you all can try it if you want to while you're on break. Okay, so take a break and maybe look at this problem right here. Maybe I'll move it up to where you can still see some of the math that we did here. I'll put it right there. You can't see it unless I make it smaller. I'll just zoom out. That should work. Okay, leave that there. We're gonna look at this when we come back. We'll take a 10-minute break. No, the video's not today, Evan. It'll be in 2 weeks. We have to talk about electromagnetic waves and the Poynting vector before we can watch that video. I mean, he's gonna explain them in the video, but we might as well do it in class first, and then we'll do it. All right, so break until... That video, by the way, is all about how... Did you watch over the weekend, Justin? Do you believe it? Do you believe what you saw? Do you think he's lying to you? It's hard to believe. I love Veritasium too. I think it's really good. I don't know what to think after I watch that video, to be honest, which is why I really want to watch it with y'all, because it's something that I've thought about before. It's something that comes up in... Anyway, I'm getting ahead of myself. Let's take a break.